Let's start by reviewing the sign of work. If you have force in the same direction that the object has moved, that's positive. We would say that the force has caused the object to speed up, which is obviously the same as the energy being transferred into the system. So this was positive. Now, negative work is when force opposes the motion. And in this case, you see that the object slows down and that energy is being transferred to the environment from the system. So energy is transferred out of the system, so this is a decrease in the energy of the system. Remember, where these signs are coming from is that work was equal to an integral of kind of this dot product. We only had to do the integral if force was not constant. So in the case where we have a constant force, which is a nice simplification, it's the dot product between your force and the displacement. So remember that the dot product is effectively the magnitude of one times the magnitude of the other, cosine the angle in between them. So if they're parallel, great, this is just this multiplied by that. If they're opposite, like this, then you get a minus sign. So remember that that's where our sign convention comes from. There's no coordinate system that actually defines your sign convention here. For work, these signs are always true because it relates to the energy of your system. So please be careful about that. So let's calculate the work done on the gas. And remember that we have to make it really clear what our system is, and in this case we're going to say that the system is the gas. So what we're starting from is that work is the integral from some initial position to some final position of some force, and then we're integrating over the distance that that force acts on. The s's all represent some coordinate in this case. So because we have s and ds, if these are in the same direction, we don't actually have to worry about cosine of the angle, we just have to get the sign right. So let's think about what's going on. We start with our piston full of gas, and there's this piston here that defines the edge. And so we're talking about this system. So the external force is acting on the gas. Now, it seems like it's acting on the piston, but the piston then acts on the gas, so it's the same thing. And in this case, we would be thinking about the direction in the x direction. So our s's are going to become x's. And we see that my external force is pointing to the left, so it needs to have a minus sign. But we would say that my piston is in equilibrium. My piston itself is not accelerating to the left or the right. Now we can say that the piston is slowly sliding to the left, but it could be doing that at constant velocity, which means that it's still in equilibrium. So because of that, we say that the force external is equal in magnitude to the force that the gas is pushing on the piston. So what force does the gas push on the piston? Well, the gas has some pressure P, and the piston has some area A, and the definition of pressure is force divided by area. So the force that the gas pushes on the piston is simply the pressure times the area. This minus sign is simply coming from the direction. So now, what we do is we think about a little bit of work, because your pressure is actually going to be changing. So we can't say that pressure is fixed and just plug this in here. We have to think about a differential amount of work. So this is going to be as the piston is actually moving a really small amount. Okay? So we're going to have a really small amount that the piston has moved, and that's going to be dx. Okay? And so we can either think about this in terms of the gas expanding or the gas being compressed. And so if we use a positive sign for dx, we're actually talking about expansion of the gas. That's still going to be helpful. So think about it that way. We're talking about the piston expanding outwards. So we actually have a positive dx, since again, remember the x-axis had 0 over here, positive over here. And so our differential amount of work is going to be F external in the x direction times dx. Now, we already said that our F external was negative. So we don't have to add another negative sign here because that appears here when we plug in for this. So keep in mind that we don't have a minus sign here because it pops up here. So in the x direction, F external was equal to negative PA, and in here this is a one-dimensional problem. We have no other directions to worry about. So we now have a tiny amount of work done is going to be equal to the pressure at that point, at that moment in time, times the area, which is fixed, dx, that tiny amount that the piston has moved over to the right, and we have a minus sign since our force is pointing in the other direction. Now, let me just do a little bit of grouping for you and show you that A times dx is actually a change in volume, right? So the tiny change in volume for the gas here would be the area, the cross-sectional area, times this thickness, which is equal to dx. So I can actually re-express this differential amount of work as a differential velocity, sorry, habit to call V velocity, volume, still multiplied by the pressure at that point. So now I go back to my work equation, and because I've transformed ds, which had become dx, into dv, I now actually have my negative integral from this minus sign here, multiplied by p dv, from my initial volume to my final volume. Now, there's a few things to be careful about. One, we have defined this to be negative, and that's important. We'll talk about what that means. And two, this pressure is possibly changing. If pressure is constant, you get to pull it out. But if pressure is changing, then you need some way to actually rearrange this integral and either change how you're doing the integral, or you can re-express pressure in terms of volume. So we'll talk about that next, and that's actually a big part of what we're doing in the remains of this chapter. However, make sure that you understand that P is not always constant, and remember this minus sign.